Am I audible? Anyone, please? Deepak? Hello? Am I audible?
Yes, sir.
Okay, thank you. Okay, so today's class we'll be discussing about open acceleration or open ACC. What is open ACC or what was the need for open ACC? Because already we have learned two languages or two compiling techniques for that matter. One was with respect to the GPU CUDA, the Computer Unified Device Architecture. So CUDA is a compiler. There is also some inbuilt hardware architecture that may support for the just-in-time compilation and building. So that we have seen in the CUDA compilation. Then the later part we moved on to some other architecture like OpenCL, Open Computing Language, where again a set of directives and libraries were built in for supporting for parallel computations. Because CUDA was basically meant for the NVIDIA or the single vendor oriented GPUs or graphical processing units. Somewhere whenever people wanted to shift or have a more portability access with respect to code they are writing. Um, so Kronos Group or Apple, developed by Apple and maintained by Kronos Group or maintained by OpenCL, we discussed something about that, where the main issue is again you can write this, something similar to the Coda, but now we have OpenCL APIs, which are more portable compared to the say specific or vendor specific compiler, something like a CUDA or NVIDIA CUDA architecture as such. So whenever we are moving on to the next stuff or the OpenACC or Open Accelerator is whenever a programmer or developer foresees a code where he can think of parallelization, so he can call OpenACC, which are again with the intention of more portability issues as such. The code should be more portable, or you can say that there's a technology development map or the learning curve should be as simple as possible. What do I mean by that? Learning curves should be simple, and how OpenACC helps to that is basically whenever you are asked to write a code, most oftenly any programmer would start with his sequential code, right? So that happens even in any C, Python, or whatever the language you are writing. So if there is some annotation that can be followed later part, the same sequential code can be converted into the parallel architecture or wherever you can export parallelism. So with refer to that, the parallel constructs or the libraries or the APIs were developed and they fall in the category of Open ACC or Open Accelerator. So a common directive programming model for today's GPUs, so everybody can use it. Was announced in SC 11 conference. So what is that? In November 2011, and they formed a conference and they released Open ACC APIs for that matter. What was the major concern? You have to code for GPUs or parallel architecture or concurrent programming. So portability in that should be the major concern. And the teammates were basically NVIDIA, Cray, and Portland Group Incorporation (PGI). These were major players, and the funding was majorly with respect to CAPS. So multiple compilers offer portability, debugging, and performance. Whenever we are discussing about compilers, so OpenACC or OpenCL or NVIDIA, so these are the somewhere supports or the APIs, application program interface providers or the libraries they are giving. So you may just have to include that hash include CUDA.h or OpenCL.h or OpenACC.h before you start using the libraries or the APIs inbuilt within them. Then, how does OpenACC is different from CUDA or OpenCL? Is basically is with respect to the, so you are going for the directives or the compiler directives. If there is a parallelization of the hardware is having the GPUs or devices meant for parallelization, then the code can compile to that because it's a compiler directive and forces and ultimately compiles to that parallel architecture. If it is not available, it can simply run as a sequential code as usual. So the compiler need not be specifically OpenACC code. Majority of the cases, unless in some of the cases there can be exceptions, the code may not run correctly, or the may not compile correctly, or may not yield the same results as the parallel code as such. So there will be exceptions, but majority of the compilers, whenever you don't have a support for OpenACC, it can just simply ignore the OpenACC directives with which they are intended. So basically, you develop a code with a sequential mindset. Then later part, start annotating it wherever the parallelization is required as such. So the history, PG Accelerator developed in 2012 or 2011 it happened, and these were the play major key role players as such: NVIDIA, Cray, PG, and CAPS. Okay. As stated, compiler portability, you can have a different compilers for that matter should support the same directives of Pragmas. So Pragma is normally used to state that the compile has to see some other libraries for compilation. So it involves some compiler directives for that matter. So majorly, whenever you see the OpenACC, Fortran and C, C++ are discussed in the slides as such. With respect to our syllabus, we will be restricting ourselves for C, C++ directives as such. Standards and compilation test suite. Device portability designed to be high level enough support to today's or tomorrow's any accelerated GPUs or devices that are possibly inline as such. So there is a standard formation or compliance formation that is well built. Annotated code, well written code should perform well either CPU or GPU because it is not targeting any particular device as such. It's still heterogeneous computing. That's what is being targeted, and that has to be supported. So as we have seen that in whenever the Fortran code, so $ACC is a directive clause. After that, there are some parameters which can be passed on for the compiler direction, directives for the compilation as such, matching directives. So hash pragma is a directive for the C. Upon that, you are including OpenACC or the ACC compiler, and then include a directive which states to do what to do as such. So you want to have something like a parallel, or you want to have something in a loop level of parallelization, or you want to copy the contents from the device memory to host memory, host memory to device memory. All that, whatever was a detailed architecture in terms of CUDA, now becomes a simple directive if you are passing the same parameters with respect to the parameters as such, but CUDA malloc, CUDA free computation. So where it has to do that. So all that is now somewhere diverted to the compiler rather than the programmer. So programmer is pushing some of his burden onto the compiler as such. So ACC kernels are similar to parallel, but loops within a kernel's regions can be independent kernels rather than one large kernel. So there is a feasibility of making that single loop into splitting. So how much should be sequential, how much should be parallel, whether all the threads or core should execute it, or only some of the threads should execute it. So all that functionalities of the parallelization on the command of a developer programmer, so can be done with respect to pre-compiler directives or the APIs, how appropriately we can use that directives as such. So what is kernel? Whatever you are intending to run as a parallel, so normally you regard as a kernel as such. So you are iterating some loops. So you are assigning something, a parallel function that runs on the GPU is normally is a kernel. So ACC kernel normally it's a Fortran code if it is a C code. So you are making it with respect to floor basis as such. Okay. Again, before I go back to this latest. Okay. So how do you accelerate the applications? There should be libraries. So you want to have a libraries developed. So all the, if I say that what is the library, if I say that I include stdio.h, so all the functionalities with respect to standard input output devices, printf, scanf for all my keyboard, monitor, and whatever is required for human interactions as such, they are well built, and once you include that, you can directly start using the printf, scanf kind of stuff. So compiler directives is basically with respect to um, uh, so hash define or macro, whatever to say that how the code should be compiled uh, is dealt by compiler directives. As we are stating that hash pragma, now this has to be moved on to the device and it has to be executed on devices. So whether it is a ACC parallel loop, copy in, copy out. These are the compiler directives which will foresee that what has to happen over there. So programming languages, Fortran, C, and wherever the support is available for parallelization of things. So most flexibility can be exploited from the programming languages. But so as of now, we are discussing OpenACC or the compiler directives for that matter. What it is, a directive-based parallel programming model designed for performance and portability. Performance is again, you can say that maintainability of the code, so that there can be a legacy codes which you want to maintain, that you don't want to, or the programmers don't want to rewrite and the entire stuff onto the sections as such. So whenever they think of that kind of aspects, moving legacy applications, you just have to annotate here and there and make the code run in parallel or improve the performance as such. So again, it depends whether you are really improving or not. So depending upon how effectively you are using the APIs. So whenever you look into the directory, say hash pragma ACC data copy in. So copy in and copy out are the directives which are stating that so how the things from host machine to device machines, that data can be moved in and moved out. So whenever you initialize parallel execution, so where or which part of the code, so whenever you say hash ACC parallel, so starting from this brace to the end brace, or wherever you end this hash pragma ACC parallel, so after this whatever comes out will be executed in parallel. It will be sorted out for running the code in terms of parallel execution as such. You want to execute this loop on a gang vector. Again, basically gang is can we have a some synonyms with respect to the CUDA devices, because you have learned CUDA first. So gang of work groups, or the basically that means blocks. So basically you are defining gang number as a grid number. So once you have a grid number, so how many blocks per grid, and work items or work groups. So gang of workers, that is what is the nomenclature that is being used in OpenACC directives. So he is planning for how effectively you are distributing the parallel work across blocks, then say the grid, block, and warp. That's what is planned in the OpenACC. So they can be incremental, single source, interoperable, performance portable, secure GPU, many cores. So whenever you look into that aspect as such, what is meant by incremental? Maintain existing sequential code. So what is incremental is basically, as we have stated, there can be a legacy code which you want to parallelize, or normally you want to make the learning curve of any new programmer or new developer for that matter, because we are practiced into the normal sequential thinking mode and sequential code writing as such. Once you have written and once you give profiling of your code, you come to know that which code can be really parallelized and how much time is being spent on each loop as such. So whenever you look into that aspect, uh, uh, so then parallelization can be visualized. Okay, so you can annotate, use the appropriate APIs, and make the same stuff or the sequential code work as a concurrent code or the parallelization. So some stuff which can run onto the host machine will run on the host machine, which you want to impart onto the devices, or the plan to run onto the devices, that can be made just annotating the same sequential code. So if at all you compile it and there is no hardware support, or no support of whenever you port the code from one board to another board as such, or there are no GPUs, so still it can run as a sequential code. Fine, same code or single source. So after verifying correctness, annotate more of the code. So they can go on building incrementally or making more parallelization usable with the same sequential code. Single source, rebuild the same code on multiple architectures, because the same compiler compiles with the stuff. And in CUDA, it was very explicitly you have to mention how do you plan your what is it, grid, block, thread, and other architectures. Now you can plan it here as well, but if you are not giving any numbers of gang of what is it, work groups, or gang of workers and warps. So whenever you are not giving that, it is runtime CUDA compiler will take a decision, so and make the appropriate numbers. So compiler is capable enough to determine how to parallelize the desired machine. So now it is up to the compiler, or compiler decides how to establish that context. In terms of OpenCL, we spoke about context, or in terms of CUDA, we spoke about what is it? Uh, Grid, block, thread, warp, and so on. So sequential code is maintained. Low learning curve. Low learning curve is because, as you stated, OpenSSL is meant to be easy to use and easy to learn. So only some few annotations. First, write a sequential code, then annotate it according to your so incremental development can happen. So program remains same. So you are familiar with C++. Yes, you can fairly write a code for whatever the functionality you are writing, and new details as you have to learn more APIs or more explicit in terms of a coded device. You can be less explicit and still use benefits of the parallel architectures. And that's where low learning curves comes into picture. As and when you learn, you can put onto the incremental architectures as it. So you start with the sequential code, begin working with the sequential code, and as a sequential code, whenever you just include that, the remaining part of the code, say for loop or whatever the loop of the code you are planning is still a sequential code. Now I want to execute this loop because I foresee that whenever the profiler is run, you may see that there is a data level parallelism or the data dependency is not there. Then entire code can be executed on to the devices if they are available. Just adding hash pragma ICC parallel loop construct for this particular loop. So entire for loop, whatever is written over here, will be run onto the parallel architectures. So parallelize it with OpenSSH, rerun the code, verify the correctness and performance. So you know the results, and once you run it as sequential code, another time you run it as a parallel executions, including the annotations of OpenSSH. So OpenSSH rightly now on the supported platforms. So whenever you say NVIDIA CUDA is NVIDIA, and OpenCL is most often supported by whatever the number of platforms you are seeing. But OpenSSH is targeting what it is stating is basically compiler will take most of the care, but yes, you have to be careful about what you are doing whenever you are coding for, whether it's a parallel or sequential, whatever the manner. The programmer should is a final control, or he should command at last. So whether it is correct or not, he knows better. Ignore your OpenSSH code additions so that same code can be executed for parallel or sequential execution depending upon your requirements, depending on the which architecture you're using, whether it supports or it doesn't support as such. So how it is being run, again there's a SSH kernel, so host machine and host kernel, parallel hardware and parallel that's memory. So basically we have to if I go with respect to textbook as such, then I have to discuss the execution model and memory model and then follow the stuff. I don't know whether they come what sequence over here. Let's see. So directive based HPC programs are the high performance computing. Whenever you say the HPC, so these are the apps which will be using the HPCs. So just for your information, so that you are aware of what is happening across. Okay, this is marketing stuff. I just skip it. Come back to it a little part after this open syntax. So again, I come back to this slide. So in any GPU, whenever we were executing, what was being done is you have a code. So any CPU will have a main memory, and there's a host memory, and there is a GPU memory. So then there's a memory transaction host machine to copy the data from main memory to GPU memory, and CPU instructs. So there is a kernel which has to be targeted to run onto the devices parallel. GPU executes them and parallel, and once the results are ready, then the results are copied back from GPU memory to the CPU memory, the host memory. So this is what is normal execution. That was whatever we learned through the CUDA, when because double underscore global double underscore, this is the kernel, and this is a kernel invocation with appropriate number of grids. So number of blocks and number of threads per block. It's explicit. So you whatever you are doing is you are saying that CUDA malloc, CUDA mem copy, where it has to copy and how it has to copy. So there's a host memory, there is a device memory, and very much explicit. And anybody who is learning that will know to it. What is the other way to develop applications? You start using OpenSSH direct. As we have seen, its incremental directives are the easy path to accelerate computing intensive applications. So you can go not all at once. So you start kernel wise of the divide that parallel chunks and then apply OpenACC directives to them and then see whether the results are correct. Then go ahead with respect to the incremental changes. So it is open is open GPU directive standards, so that it's nobody's proprietary and everybody is contributing to it, and you can use it. Allow complete access to the massive parallel powers of GPU. So whatever is available in the architecture can be utilized. So depending on the compiler is capable to use it, and the hardware is ready to cater it. Okay. So simple compiler hints. So simple compiler hints is basically I'm saying that this has to be compiled as a kernel, and there's a prescriptive and descriptive kind of indicators whenever you start using kernel and parallel kind of approaches. So what he states compile hints is compiler may say that consider using these hints, or compiler is free to ignore that. So ultimately it produces a error. So there is a functionality written for any application. So after that you check whether the code is correct, and if something is neglected or whenever you compile it, so the pros and cons can be discussed. So the messages are passed whenever the compilation happens. So how it is compiled and what was the intention of the programmer's stuff, and what is has really done will be shown to the what is it, programmer, so that he can decide which was really better. What is major advantage? So unlike NVIDIA CUDA, so you can work across the different GPUs that are possible. Basic steps to get started: annotate source code with the directives. So what is the directive? This is again a Fortran code he has taken. C code is basically you say that hash pragma, OpenACC, then kernels. Okay. So alpha x plus y, or there's some simple code this he wants to implement. So parallel C code whenever you want to implement. As we have stated, hash pragma is the compiler directives. So it is using OpenACC's so parallel directives. So this code has to be compiled as a kernel. Now, when I say that it has to be compiled as a kernel, this code will run for I device, or the whatever the n number of devices parallelly that has to be executed. Okay, parallel Fortran code. So similar stuff, but now this is a Fortran syntax that has to be understood. So clauses. So as we have stated, whether you are using copy in, copy out, or the different directives for that matter. Okay. So I just skip for the Fortran code for that matter. So if else conditions, you can even speak the asynchronous communication between the data movements between the host and what is it, device memory as such. So again, you may want to say that something after computations you still want to retain that. Normally what happens is whenever the parallel computation is over and all the allocated device memories are vanished, so you normally want to free them. But if there is a say what is it, the same values are to be reused, something like a shared memory in terms of coda, and there are constructs to make it happen. Okay, these are the compilation directives, so that your GCC compiler will have a switch minus SCC, so that it will comes from that. Apply the ACC compiler. So whenever you find a time, so browse through your man GCC or GCC options. So different architectures. One of the switch says ACC, which where you will be compiling this piece of sxpy.c, resulting into the object file as sxpy.acc, with compiling with respect to the using the ACC directives as well. Okay, so this is information what is compiled and how many registers of the build information that is for showcased as such. Again, okay, I will just state this. So he's taking Jacobi iterations. What is Jacobi iteration is basically 3 cross 3 matrix, and the central pixel is nothing but average of all the 9 pixels. So if I can, so that's what is code is written over here. And the scalar he is multiplying with respect to that. Otherwise, Jacobi iterations of the Jacobi averaging is with respect to. So you have the 3 cross 3 mask and the center element you are computing. So we have seen that already in one of the previous chapters. Okay. So iterate across matrix element, calculate new values from neighbors, compute matrix errors for conversions. So this is what we want to accomplish. A normal C sequential code is being written, now that has to be parallelized. So whenever you want to parallelize, he starts with hash pragma OMP. Again, yes, we are discussing OpenACC. Open OMP is open platform. So whenever you have multi-core CPUs, so whenever you are planning for Intel i3 or the multi-core eras, we are not speaking specifically with respect to the GPUs as such. A parallel architecture within a CPUs, so multi-core CPUs. So then OpenMP is a platform where you start executing these with respect to OpenMP. OpenMP is one more API provider of the standard where you start writing for parallelization within a CPU core as such, or with same host machine. So whenever you say that, a global memory concept of the device memory, host and device memory will not arise in this aspect. Uh, Execute GPU kernel ACC. Now whenever you look into this code and this code, now you can see that hash pragma ACC kernels. So this for loop whatever, so it is a reduction clause again he is using. So this for loops, because initially this pragma is applicable for this loop or this kernel as such, and anyway the internals, so this entire loop or whatever the number of lines this consists of will be executed on GPU kernel. So again, this can be one more loop or the parallelization that can be executing. Whenever we are stating that, we are not mentioning gang numbers. Again, we'll have the one more discussion or one more class on this. There will be discussing what is the number, what is meant by number of gangs and number or the execution model and memory model to be very precise as such. Okay. Quote unquote, I'm just introducing it at this juncture, right? This class as such. So data management, you can move asynchronously from host to device machines. So management data movement, data regions may be nested. Clearly, there is no strict bifurcations with respect to synchronizations apart from the fork and join kind of architectures. So what is meant by fork and join? So a single kernel runs and then it splits into many other kernels or many other threads, so that they are running threads or they are running in parallel, and finally they will converge to make it happen again to the some running of sequential code for that matter. So these are the data clauses. So copy list. So whether we are copying allocates memory from, you just note it, GPU to CPU, CPU to GPU. That is happening whenever you are using this. So these are the APIs where as in case of CUDA, you are really has to mention that you just have to reserve a space. So CUDA malloc, then CUDA mem copy. That means you copy that, then you compute something, and again CUDA mem copy from say earlier it was from host to device, now it is from device to host, and free all the memory pointers whatever you have allocated. So whenever you start using this, in case of open ACC APIs, you need not worry about how it is done. Whereas in CUDA code, you are explicitly should know how to plan about that particular memory. So you still use the memory pointers, the first element of the memory, or the say pointer or zeroth element, and the what is the size of that pointer is pointing. So array has to be precisely mentioned even in here, but malloc, calloc, say malloc, free, and computation, you need not worry about. Okay, so allocates memory GPU but does not copy. So you're just allocating mallocing. So data is ready, present or GPU from another containing data region. So present, you want to retain that. Okay. I'm not going into details as such, but there are data clauses. What they are doing is they are hiding or they are creating an abstraction where a programmer is free to do that. You just annotate it. How it happens, you need not worry. So the programmer or compiler will take care of that allocations as such. If you are already well versed or a good programmer, you know that what to be changed whenever you compile, build, and see the results, what is being executed. So zero size and what is being transferred copy in and out. So how do you provide the parameters for them? So data OpenACC hashtag is compiler directive, ACC is OpenACC directive, and data inside that whatever the copy in and copy out you are using. Okay. So Jacobi kernel, as I stated, it's normally averaging for that matter. Now you are making that reduction and things available for that matter. So global memory is a RAM CPU server and both GPU and CPU currently up to 6 GB, and he's just making it realistic or more realistic numbers can be sought as such from these slides. Nothing very specific to OpenACC is stating. Streaming multiprocessor and streaming processor, that's a normal GPU architecture. He's again repeating that. So for me, one of the GPUs has taken as an example, has 32 CUDA cores for first streaming processor, 32 floating point operations per clock, 64-bit floating point operations per clock. So basically floating point 32, floating point 32, so single precision and double precision. That's what he's stating. 2 warp schedulers and so on. So cache and other architectures for that. How do you invoke a CUDA code? So basically you call that as a vector invocation, and how do you write it? Double underscore global, that's how the CUDA is being written. So he's repeating that stuff. We just want to skip that. Okay then. So any doubts until here? So we can take up the remaining stuff in the next class. Okay. So I just see that anything is there. Anyway, we are using terminologies as such. Now to be number of gangs and worker and vector. So I just want to finish off this execution model, memory model for that matter. Okay. Anyway, I will see this. So gang is the highest level of parallelism, so equivalent to CUDA thread blocks. So number of gangs are basically CUDA grid. How many blocks in every dimension as such is normally referred as a num of gangs or the number of gangs. So gang loop affects the CUDA grid. Okay. Worker, a member of gang equivalent to CUDA thread within a thread block. Number of workers is nothing but a thread block size, and vector is nothing but a block size. The tightest level of SIMT, or the single instruction multiple thread, single instruction multiple data of vector parallelism is roughly equivalent to CUDA VAR for SIMT vector. So one issue or the one instruction decoder and issues a command, and there are multiple units which can execute that. So a single instruction multiple data kind of architecture is supported. That's what is being stated. So cache and directives, I'm not interested in this right now. So it is okay. This is what we have discussed. If I want to discuss exactly the syllabus research, no, I just want to work. So this is OpenACC execution model. Accelerated the device to GPU. 3 levels of parallelism can be seen over here. So one is execution units. So there are execution units and multiple threads within execution unit as such, and vector operations within each thread. So this is 3 levels of parallelism that can be seen in Open ACC execution models as such. Then there is no proper synchronization methods available with respect to OpenACC. Only fork and join. So you fork a particular code, and that the fork, so that thread starts running onto these devices, and whenever they finish off, all that threads converge, so or join together, and then produce the final results. Can run as a parallel or kernel kind of constructs. So what is meant by parallel and kernel kind of constructs, we will discuss in detail in later parts. So one is slightly descriptive and prescriptive. Descriptive is up to the use write it. Say prescriptive is you are compelling the compilers, or programmer is demanding, I know what I'm doing, so you just do it. That's what is meant by prescriptive. Whenever you say that this has to be done in parallel. Kernel, whenever you are writing that, it is up to the compiler to decide whether it can go into parallel. That's roughly at these things I can state about that. Group of gangs are basically kernels, and group of workers are parallel ops as such. Okay, that is your execution models. So whenever you look into the memory models, so similar to the CUDA or any other GPU architectures, there's a host memory and device memory. They're totally separate, and only there is some difference is stating that whenever you start using CUDA 4.0 devices onwards, so there is a unified virtual addressing, and hence you can allocate some memory onto the host or device because there's a virtual memory addressing or the unified virtual memory addressing. Um, Weak consistent for memory. It's not consistent memory as such. There is no proper mechanism for the because whenever you are working on to that, there is no methodology directly I can access the device memory or the host memory. So whenever you want to access that, you are having the copies or there is a notion of the coherency is somewhere missing. So you may be working on a copied content of a so some memory content copied from the device or host whenever you are working. So you are working on a copied content, and there is less of coherency aspect as such. There may be some hardware aspect or hardware memory accelerators or modules may be supporting the to establish a coherency by having that invalidate and dirty bits as such. Otherwise, from the compiler perspective, whenever you see it, there's a weak memory fencing available. As in case of OpenCL, you would have done some fencing in the same memory so that only the blocks or the threads in the same group can access that shared variables, and something of that can be established that is not clearly seen in terms of OpenSCC memory models. Okay. Yeah. So next class, I think I will start with this, and we'll maybe one or two more classes. We'll finish with respect to OpenHCC chapter as such. So I just want to close for today. Any notes? You are welcome. Okay then.